Okay, welcome to the stream. We're doing part 3 of the Python driver. So I've done a lot of the development before this. So we're going to try to do a quick overview and show you how the driver works in action. So a quick review. We have a PCIe system. I'll bring up the Vivado block diagram. So here we have the PCIe block connected to an Axi bus. This Axi bus is connected to this switch, and the switch has various peripherals. We have a hardware ICAP, which we use for we use for reading the ID code of the device and doing a warm boot. So we have Xilinx XADC, which gives us a temperature. We have a debug bridge, which allows us. I'll show next recording. We can look at how that debug bridge works, and then we have this Axi extension where I can edit the top bits of using the GPIO here. I can edit the top bits of the address bus, and we use this to page into the DDR here. This is very useful. And then there's also the quad SPI where we can go over some of the functionality. So that's kind of a review of the block diagram. Nothing too complicated. We have a microblaze that's running local software, and these are my designs under test that have their own little locations. And other blocks, it's just clock reset. So yeah, it's mostly we have the kind of the main PCIe bus, the microblaze using the data peripheral bus, also connected to the same thing. So everything the PCIe can do, the microblaze can do. There are some updates I want to do to design, but let's go ahead and show these videos of how my hardware and software works on a Linux system, and then we can go from there. Okay, what's next? So first video, we did ICAP, we read the ID code, we perform a warm boot. Second video, we reset the XADC, which you have to do when you do like dynamic partial reconfiguration. Temperature's going good. We have the QSPI. My devices have two different parts. They have different array sizes. We just did a little bit of a verification. We haven't implemented a full read and write yet in our new Python API, but that's in the steps to do. Today, we're going to talk about the DDR paging. So first, let's go bring up what our software looks like. Okay. So we have our PCIe device. So our PCIe device has a debug bridge at this address, the DDR page address. This is the microblaze debug module. Oh, that's for the UART. We don't use that one. This is for doing UART over JTAG. The microblaze does that. The PCIe doesn't need to do that. The ICAP, QSPI, XADC, and the GPIO that we use for paging the DDR. And this is kind of my application code, initializing it and everything. Doesn't necessarily need to do all of that. We may edit this and throw in a I guess it wouldn't hurt. It's not going to be writing anything yet. Maybe running some stuff in the background. But we're not injecting any faults. I guess it's injecting faults. So we may, where would be a good place? Like this. We may have to move this code around so we don't mess things up for you guys. We do the rescan we want to do there, and we probably could. Yeah, we can probably just return there. We'll show how this, but our device, we have like each PCIe device has its own one of these, and we'll show how to reference it later. We have a rescan. This is just using the Linux commands to rescan a device once it's programmed, once the FPGA is reconfigured, and we can look at it. The times are a little bit playing around with that, and the log is part of the application code. But yeah, that's basically it. But so today we're going to talk about the DDR. So we initialize the DDR. We're going to set the page, the base address of the DDR. We have a device offset, a base offset, and a page offset. So the DDR. Oh, so the page offset. This is how our paging is on a GPIO. That's what that's used for. So we set page, right? So what we're going to do is basically write the address we want to go to the interesting that we're doing PCIe. Oh, is that? Yeah, it's the mem utility. So we're saying the device offset, page offset. And then we can change the page. We can read a value. We can write a value. And the paging only looks at the bottom. So besides paging, we care about the bottom 16 bits when actually doing things. So this code, yeah, we basically can access a page of the bus. So we have set the page here, and then we can take the remaining bit and we can read that address. We can write that address. We can read the whole page and write the whole page. So there's a verify option where we then read the page and compare if there's any differences. Reading the page. We can set different lengths. And then I basically have a write file option. We could read files, but we have nothing to read in my code at the moment. But this basically does page by page. And then you can pass it verify, or it then verifies the page it's writing. So that's useful, especially when I write important partial configuration files. Then partial configuration files for this. Okay, so that seems good. So I mean, maybe we'll just go through the functionality. We can go over this again. So playing around, I saw that to be able to make sure we write everything as 32 bits, because I was having an issue earlier when I was using mmap that would write everything byte-wise. We want to write everything word-wise. That's just because of how the Axie bus works, or how many of the registers inside the Axie devices work. They expecting a word write and a word read. So what we do is we take this memory map file right here, and we put it to a NumPy buffer, and this buffer is specific for 32 bits. And then we take the addressing and make it word. So we're taking byte addressing and byte access, and we're converting it to word addressing and word access. And this allows us to kind of meet the expectations of a lot of Xilinx's IP, which is very critical. So that seems very good. So what we're going to do is we're going to open up main, and we're going to kind of look at this PCIe devices, and then we're going to create a new PCIe device from here. So first, I want to show you guys the tree. So here's our LS PCIe C tree. So let me show you. So this is an FPGA. This is an FPGA. These are 3 more FPGAs. 3 more FPGAs. 3 more, and 3 more. So that's 12. That's 16. That's 12. That's 14. 14. 18. 22 FPGAs, and here is our 23rd FPGA on the motherboard. So currently I have 23 FPGAs working, and they're doing great. I have had no issues so far. There's maybe a few issues on boot up, but I'm also doing fault injection to these devices, so I'm expected to break them every once in a while. But normal operation, they seem pretty consistent. If I wasn't corrupting the FPGA bit files, they probably would work just fine. So we're going to exit this. And then I want to go to, we're going to go dev. We're going to look at this folder. Right, we want to look at PCIe device. We're going to open it with Notepad. So this one's linked to the device. What we want to do, I think we want to just put a return right here. That should be good. And we're going to go ahead and put that. I think that should be good. We have a tickle client for this FPGA. Okay, we'll save that. That way we can show you some cool stuff about messing around too much. Okay, so that's saved. And now we have main. So we're going to copy the operation that we do in here. So we're going to go Python. We're going to do sudo Python. So we're just going to do sudo Python here. we're going to import Pcie PCIe. Pcie PCIe. And then we're going to go devices equals Pcie PCIe.ls PCIe device equals 0x7024. Okay, now we do devices. Boom, we have a ton of devices, and we can be like device 0, right? Except that finish it does not have the bar. We have the different bars and the different addresses. So we have a device. So now we can from PCIe device, we can import star. We'll give us our. Oh, I'm in the wrong folder. Let's just go PTSDV. I do things wrong. So we're just going to import that again. Do devices. Then right there. Okay, cool. So this was setting up an XSDB in the background that allows us to do process debugging. I didn't think about this. How can I avoid this? Normally we can socket it. I mean, how do I put it to the background? I was doing threading in here, and threading's not really supported in here. Oops. Okay, well, we can just exit it for now. We're not using the XSDB, so it shouldn't be critical. It may cry that when we try it, when it tries to do sets up a client, but it doesn't connect to that client yet. May not. Okay, well, we'll try. Sorry, I may not have this set up. So we're gonna do PCIe. There. Oh, it's up there. Okay, so we're gonna exit real quick. We're gonna log back in, and we're gonna remove the need for that cd pytest dev. So we're gonna go back over here, and we do not want to set up a client. Because we're not setting up a client, let's go ahead and get the microblaze down. And we'll talk about that later. I might have to play around with code for next time. Okay, so sudo python. And we're going to go try this again. It's going to be so much fun. Try your best. Okay. Now we're going to now we're going to call it dev, right? We'll just call it dev. Dev equals PCIe device. It's going to be 0 for now. It doesn't really matter that. They want to do device devices, right? And 0. Boom. Going to be playing around for a few things. So right now, the first is a flash, 8BB. Those are flash registers it's reading. That's the ID code, and then it caused a warm boot, so the FPGA is warm booting, and then we read the temperature. Kind of interesting the server doesn't work in the background. So we now have the DDR. So we do dev.ddr, right? DDR. And now let's go through these functions and show you the very functions, and we can maybe look at the other ones. So say we want to read 8,000. 1, 2, 3, 4, right? And let's go ahead and read a hex value of that because that's more interesting usually. There we go. And we want to read the next address. And the next address. These are the normal addresses in the DDR when the microblade boots up and it calibrates and everything. So that makes sense. And now we can try what? Dev.ddr.write 0x 8 1 2 3 1 2 3 4, and then what we want to say dead beef. Cool. And then we go up here and read that register, and we read dead beef. Now we can go and read a different register. Affected. And so yeah, and the memory goes all the way up to, you can read the last value. Those are the same. But the high end of it is going to be BBFFF123C. That's the top word of our DDR. So yeah, we can read DDR. It's great. And it pages just fine. And the reason we did the whole paging is because the Xilinx XDMA core is huge. It takes up so much space. It was like 13,000 LUTs. And I just could not have a good reason because of my constraints of my application for this. So I dropped it down to this core. So we definitely don't have the bandwidth we can get with the SDA core or the XDMA core. But it's sufficient for my needs. I'm not transferring a large amount of data back and forth. But there's something I do want to look forward. I mean, Python's definitely slowing down the read. Python's not the best for this. We would want to do like we would want to do a kernel level driver software to see if we get the best performance. But I think I would want to look at doing another PCIe IP core, and the LiteX IP core for the Vex RISC-V processor does look promising. So I am interested in looking at that. So there's the DDR read writes, pretty simple. So let's go look at the other devices that we talked about. So let's go ahead and pull up the iCap, right? So we can do iCap read ID. I really should get like IPython notebook pages working for this. It'd be so cool. So there's the ID code. I read that through using all this fancy stuff. Don't want to W star it, but yeah, we just have ID code, W star, resync, reset. This is resetting the iCap core, not resetting the FPGA. We have a few registers and masks for those, basic stuff. Now, if we go to the XADC, we have a read temp and returns temp. So I think we want to do what dev.xadc.read temp. Boom, we read the temperature. Pretty straightforward. Okay. Now we want to look at, is there anything on the QSpy we can do real quick? Yeah, we can try QSpy, right? So we do dev.qspy.read ID. I'm not happy with that read ID. I gotta see what's up with that. If we do, what if we do a reset, right? Reset, and then we read the ID. I read the ID correctly the first time, so there's probably an issue with this. I probably have to do some type of desync or clean. Or maybe the FIFO's not being cleaned out properly. I should look at looking at that later. Info read. So this info read, or the device info read, right? It's device info read, I think cleans out the FIFO. Yeah, see all those good values. But yeah, see there's something, it's rotating values. It's like, it's not cleaning out the FIFO every time. Read ID, read ID. Let's see if we do a reset and device info read. I assume we just do a reset every time then. We want 21, so 16. Can't remember the importance of those values. Where that would be the 8 or something. Read ID. Yeah, we got something that's not being cleaned out properly. So if I do, should I do a reset and we do this, right? We get a 16. Where's the 16? So it might be one too early or something like that. Yeah, so we'll have to clean up the read and the writes on this. We're getting close, but there's something we're just missing, and I have some other code I can reference. So let me clean up this before I do. I want to get the flash reads and writes going pretty well. So that's basically all we can show. I kind of wanted to show you guys the what we have working on this. It's kind of interesting. So we're going to save the main thing. So let's exit here. Okay, I had the socket in the background. Oh, cool. So let's show you how the system works. So we're gonna screen, and we're just gonna show you what my system is doing on boot up, and then we can go look at it. So we have the XSDB. This XSDB is how we're going to connect to the 23 different processors. And so this is the first FPGA. This is the PCIe location. This is reading the ID. That's the proper ID, but this value is expected. This value is expected, but the reads don't seem. I need to go look at that. So we're downloading the partial bit streams here. We're establishing the microblaze, the Xilinx virtual cable. Programming the microblaze, having the microblaze run, and it's super happy. Okay, so we have this. So we're going to detach the screen, and then we're going to open up an XSDB window. Do I need to reference it? We might need to reference it. You can do that, right? It's going to be the tools. Xilinx hardware server 2000 bin SDB. Boom. Okay, we're in XSDB. We connect. We hit targets. So what's happening is we're slowly making targets. We have 2 targets here. Maybe programming them or whatnot. Now we have 3 targets. And if I do JTAG targets, we have these Xilinx virtual cables at different local ports. That one is, yeah, that one's going to be connection refused for a bit. And this is how we're going to be able to program the 23 FPGAs. And so next whatever time that video happens, I'll talk about how to set up the XSDB to do a Tickle client, a Tickle server client through Telnet to connect to it. And how to set up the Xilinx virtual cable. We can go through that code next week. It's really interesting, and I'm able to debug the microblaze on 23 different PCIe devices at one time, all through Python, all automated code, and automate the process. It's really cool, and that's kind of why I have the show today. We can go through that later. But yeah, thanks for watching. It's been a while. I've been very busy. This is more of a side thing, so don't expect much. Feel free to ask questions. My goals are I'll probably do YouTube streaming from now on. I think when we hit 1,000 subscribers on YouTube, I will set up a Discord. Seems like an appropriate time to do that, and we'll see where we go from there. So far, we'll continue with the PCIe Python development, and after that, I want to look at doing a Visual Studio GUI for the from my Xilinx my Xilinx UltraScale Plus product, the VCU 1525 or the VCU 1525, and show how that works with Visual Studio and how you can do like maybe a simple GUI to maybe do some DDR test or something like that. But yeah, thanks for watching. Bye.